Hello everyone, welcome to video 1 of chapter 3. In this section we're going to get into the idea of a vector quantity and what we can do with vector quantities. So to look at our guiding questions for this video, we want to know what is a scalar quantity, what is a vector quantity, what are the properties of a vector, and how is vector addition and subtraction performed graphically. We will continue on these ideas in the second video when we look at taking a vector and breaking it into smaller parts, and ultimately we'll use these vector ideas in our third video when we look at the idea of projectile motion. So, what we want to do is start off by looking at what is a scalar quantity and what is a vector quantity. Well, in science and math, a scalar quantity is any measurement that only has a magnitude. We're only focusing on a measurement where there's just a size and that's it. It's just a number. And generally speaking, there's no direction with it. So, for instance, think about the number of students in the school. You know, we could have, let's say, 600 students, and there's no direction. We don't say 600 students north or up or anything like that. It's just 600 students. That's a scalar because there's only a size with it. Number of pages in a book. Again, there's no direction, it's just the size. Anytime you have a measurement that is just the size, just the magnitude, that is known as a scalar quantity. On the other hand, when we have a measurement that requires some type of direction with it, that is known as a vector quantity. A vector quantity is any measurement that has both a size and a direction to it. Both need to be there. There needs to be some magnitude, some size to it, and there needs to be a direction with it as well. For instance, think about our discussion of displacement from the last chapter. We said with displacement, in addition to there being some distance you move, there's also a direction you move. It could be you moved 5 meters west. It could be you moved 10 meters north. Whatever. There's a size and a direction. So, when we talk about measurements, we can say every measurement has a size. They all have a magnitude. But vectors have a direction. So one thing you want to be able to do is look at a measurement and decide, okay, is this a scalar quantity? Is it just a number? Or is it a vector? It's a number, but it also has a direction with it. So if you look at these 5 quantities we have here, distance, speed, velocity, time, and acceleration, take a moment, pause the video, think about what each of those quantities is. Is it a scalar or is it a vector? Well, let's take a look here. Distance is scalar. Remember, we said distance, we're only concerned with how many steps we actually took. So there's no direction, we're just worried about how far. So that's definitely a scalar. Speed is kind of the same thing. Speed is distance covered over time. So that's going to be scalar. We're not worried about direction, just how far and in what period of time. Velocity is a vector. Velocity uses displacement. With velocity we have a size and a direction. Therefore, it's a vector. Size and direction, those are the 2 key things for a vector. Time. If we think about time, we don't measure in negative seconds or anything like that. And we don't have a direction of time, so to speak. Time is a scalar quantity. And if we think about acceleration, well, that can be speed up, slow down, change direction. Remember, changing direction, that's a vector. So acceleration is a vector. So now that we have those down, what we want to do is look at some properties of vectors because that's going to lead us into what we can do with vectors. So first of all, how do we represent them? Well, there's 2 ways we can represent a vector. There's the text version, which is what is used in textbooks and scientific papers and things like that. And we also have the arrow approach, which is more common when we look at diagrams when solving problems. If you're reading text, you can represent a vector in one of 2 ways. One, you can make it in bold print, which is kind of hard to do when you're writing, but textbooks often use this approach. For instance, you might see velocity represented by a bold V. On the other hand, if it's a scalar, they are actually represented by an italic letter. So notice speed is an italicized V. So bold is vector, italicized is scalar. Another way you can represent a vector is by putting an arrow on top of it. So, for instance, you might see acceleration like this. It's the letter A, but it has a little arrow drawn on top. Anytime you see the arrow, that means it's a vector quantity. Now, that's nice, but for what we're going to be doing in class, especially when it comes to problem solving, we want to look at it in terms of an arrow. And the way we do this with vectors is we have the size and direction. Well, the arrow is going to point in the direction of the vector. That should make sense. If we're drawing an arrow to represent what's going on, it should point in the direction it's going. And we're going to make the length of the arrow proportional to the magnitude of the quantity. That's fancy words for basically saying that if you have a very large quantity, that arrow is going to be longer than a smaller quantity, which is going to be a lot smaller. So that's how we can represent vector and scalar quantities. So for instance, let's say we have a sprinter running with a velocity of 6 meters per second. Well, if we want to symbolize that, we could say bold v is 6 meters per second south, or we could say v with the arrow on top is 6 meters per second south. Or if we want to draw a diagram, it's south, so we point the arrow down, and then we can make it a certain length and say that's 6 meters per second. If we had another arrow that represented 3 meters per second, we'd cut it in half, since 3 is half of 6. If it was 12, it would be twice the length. Let's say we have this. Two cars start at rest. Car A has an acceleration of 3.5 meters per second east, while car B has an acceleration of 1.5 meters per second east. So, again, I included an error in here just to make sure you're paying attention. We have the acceleration of A, it says it's 4 meters per second east. It should be 3.5. For car B, it should be 1.5, but instead, for some reason, I put it as 1. So we have that. Now notice that the length of A is much longer than B, as it should be, because the magnitude, just the size of A, is longer. So keep that in mind. Again, when you draw these vectors, if it's a larger quantity, make it longer. If it's smaller, make it shorter. If we're doing this to be exact, we do want to come up with some type of scale. For instance, we could do, in this case, maybe 1 centimeter represents 1 meter per second. That way we can be exact with our dimensions as opposed to just kind of roughing it. Now, some other properties of vectors you want to be aware of. First of all, we can draw multiple vectors occurring at the same point. We don't have to try and line them up in all these different places. We can just pick a point and say all these vectors occur at the same place. It's due to the fact we can actually move them around parallel, which is the second item here. We can move vectors parallel to themselves in a diagram. We have to keep, though, the same size and the same direction. We can move vectors around and put them wherever we want, but we have to make sure the vector itself is not changed, meaning it still points in the same direction and it still is the same size. The third point with vectors we can do is we can actually multiply or divide vectors by a scalar quantity. So we could have, a displacement of 15 meters and divide it by 3 seconds. That gives us velocity. In doing so, we're going to get a new vector out of it, and what we do is whatever that scalar quantity is we're multiplying or dividing, we're going to change the magnitude in that way. So that'll affect the size of the arrow, but it's not going to affect the direction. The direction always remains the same. So let's look at a diagram to help us explain that one. So here we have 3 vectors. You can see in the middle there, we have an arrow representing a velocity, in this case v sub 2, or v2. And if we take that and multiply it by 2, we would have 2v2, which is on the right there. Notice it is longer. That makes sense. We're multiplying it by 2, so it's going to be double the length. So we have a longer arrow, but notice it's still in the same direction. We can't change the direction when you multiply or divide. It's going to be in the same direction always. Now, if we cut it in half, we have half v2, which is going to be smaller. In fact, it's going to be half the size of regular v2, and notice that is about what it is. But they are still going in the same direction. When you multiply or divide a vector by a scalar, it just changes the size. It does not do anything with the direction. Now, ultimately what we want to do with these vectors is add them and subtract them. And there are specific rules we have to follow to do this. We're going to start off with the easy method and work our way up from there. So the easy method is what happens if they're acting in the same plane. So both vectors are horizontal, both are vertical, anything like that. When we add vectors together, we develop what is known as a resultant vector. Notice that term in bold there. A resultant vector is the result of adding 2 or more vectors together. And our rule is when they are on the same axis, when they're both horizontal, both vertical, whatever, if they act in the same direction, we can just add them together, which I think makes sense. If we move 5 meters east and then 3 meters east, then we moved all together 5 plus 3, which is 8 meters east. If they're in opposite directions, we subtract. Same idea. If I move 5 meters east and 3 meters west, then 5 minus 3 is 2 meters, but it's going to be resulting east. So with that in mind, anytime you have vectors in the same plane, both horizontal, both vertical, all we need to do is just follow normal addition rule. Just keeping in mind, if they act in the same direction, we're going to add them together. If they're opposite, we'd subtract one from the other. You can see here on the video, we have this diagram. It shows a couple different vectors being added together. 5 plus 5 would be 10. 5 plus negative 5. In this case, we have two vectors of size 5 but opposite directions. They cancel out. And you can see the rest of them from there. That's the easy scenario. Unfortunately, not everything is easy. What happens if they're not on the same axis? Well, what we have to do is come up with a different way to do it. And the way we're going to focus on in this video is what's called graphical addition, or what is known as head-to-tail addition. And here's how this works. What you do first is pick your starting vector, draw that to scale in its direction. Then you're going to take the vector you're adding, the second vector, and you're going to put it on your diagram so that the tail end of that vector starts at the head of the first vector. By head, I mean the part where it's actually the arrow. So you draw that second vector starting at the head of the first vector. Make sure you keep that same scale and direction. And then you're going to draw your resultant. The resultant vector is the arrow that can be drawn from the tail of the first vector to the head of the second vector. And we can actually use a ruler, measure out the magnitude if we have a proper scale set up. That'll be something we're going to focus on in class. And we can figure out the new direction just by looking at the direction of the arrow. That's the nice thing with this graphical addition. It allows us to visualize what the new vector is going to be just by looking at the diagram. So let's take a look at this in action just so you can get a better idea of what's going on here. So let's say we're adding these two vectors. We want to do v1 plus v2. So what I'm going to do is I'm going to draw v1, and then at the head of v1, at the arrow part, I'm going to put the tail of v2, as you can see there. So we have v1. I took v2, placed it starting at the head of v1, so at that arrow part. Now, if I want to find the resultant, the total of v1 plus v2, I'm going to start at the tail of v1 and draw an arrow to the head of v2, which is what we have there. And we can label this as VR for resultant. Sometimes we can call it R. We can call it VT. You know, the name is whatever you want it to be, but that's the general process. You start with your first vector, add your second vector by just placing it at the end of the first one, and then draw your arrow. Let's look at another example. Here we have v1 moving down and to the right, v2 is moving up and to the right. So if I add v1 plus v2, I draw v1, and then I place v2 at the head of v1, like so, and then I can draw my resultant. I start at the tail of v1, go to the head of v2, and that's what I have. So that's the idea of this graphical addition. We're going to get a lot of practice in class. It is a nice skill to have because it is a good visual representation of how these vectors work. We can also subtract vectors. When you subtract a vector, all you're really doing is adding, but you're taking your second vector and flipping it around. When you subtract, you're adding the negative vector, so to speak. And what we can say then is, if you take your original vector and add its opposite, you get 0, because you're basically moving forward 5, moving back 5, or moving up 3, moving down 3, anything like that. The opposite of a vector is the same vector, same magnitude, but opposite direction. You can see there we have v1, which is a long arrow pointing to the right. Well, the opposite of that, we symbolize that by just putting a minus sign in front, is the same length but to the left. v2 is up and to the right, negative v2 is down and to the left. So when we subtract vectors, we're just going to add on the opposite vector. We just flip the arrow around and would continue on as normal. Let's see how that works. So here I have v1 and v2. Notice v1 is the long arrow to the left, v2 is a shorter arrow up and to the right. I want to do v1 minus v2. So when I do this, I'm really going to add v1 plus negative v2, which looks like this. I have v1, and then I'm going to take the opposite of v2. I'm going to flip v2 around, and instead of it going up and to the right, it's now going to go down and to the left. And then I can just add it as normal. I start at the beginning of v1, and I go to the head of v2. So there we go. That's subtraction. With subtraction, you just take your second vector, flip it around, add it as normal, you get your result. So, let's go back to what we identified at the beginning of this video as what's important. What is a scalar quantity? It's just a measurement that just has a number. There's no direction, it's just a size, it's just a quantity of something. What's a vector quantity? A vector quantity is a number that has size, but it also has a direction with it. That's the key difference. Vectors have direction, scalars do not. What are the properties of a vector? Well, we talked about a couple things. We said we can draw them as arrows. We said you can multiply and divide them by scalar quantities and get some new results out of it. You can shift them around. As long as that magnitude and direction stay the same, you can put them anywhere you want. And then finally, how's vector addition and subtraction perform graphically? You draw your first vector, you move, or you take your second vector, place it at the end of the first vector at the head, and then you draw your resultant. We will practice this skill in class, and then we'll move on to our second lesson with this, which is how do we combine vectors without having to do this graphical method. There's a little bit more math involved, but it's not too bad. I'll see you in class.